Logarithms test review. Alright, so these first three problems say rewrite each equation in exponential form. So what we're thinking about here is this inverse rule right here, right? That we can take exponents, exponential equations, and logarithmic equations, and that there's a connection between the two. Okay? That's what's going on here. That's what we're using to rewrite each equation. So if we look at this first one, we got log base 6 of 216 equals 3. So the base would be b, the number in here would be n, 3 would be x. So the base stays the base of the exponent, okay, to the x power, so 6 to the third is equal to the n, or 216. So that's all you're doing, is just rearranging them, okay? Same with number 2. Base is 64, x is 1/2, so 64 to the 1/2 equals 8. Which, if you want to double check, put in 64 to the 1/2 in your calculator, you'll get 8. Okay, now number 3, log base. Well, what's the base? Remember, when you see log without a base, it's 10. So it would be 10 to the x equals the n 100. Okay, so just like that. Now on the flip side, you just do it backwards. You take the exponent, put it in the log. So the same pieces. So 196 would be the b, negative 1/2 would be x, and 1/14 would be n. So I just rewrite it. Log of the base, 196, of n of 1/14 equals negative 1/2. So just like that. So number 5, the base is 4, so log base 4 of the n, 64, equals the x, 3. Number 6, now we have the e for the base, so log base e. Now, this is another one of those special ones. Log base e we actually rewrite as the natural log, but we put the L first, so ln. So, the natural log of the x, the n, 148.413 is equal to the power 5. So, just like that. Those rewriting ones, that's all you're doing. You're using this, so if you haven't written that down, make sure you get it written down somewhere so you have it. Alright, now, evaluating each expression. They want us to figure out essentially what the answer would be. Okay? Now, number 8 and number 10 should be really simple, because these are special rules. So the way to think about it is, number 8, there's my base of the exponent equals 7. Well, 7 is just to the first power, right? So what would this log base 7 of 7 equal? It would have to equal 1. Okay? That 1 is what goes in that position. That's what it's equal to. So anytime, another rule, I guess, anytime you have the base is the same as the number in here, it's always equal to 1. Doesn't matter what number that b is. If it's the same, it always equals 1. Similar idea is with number 10, because if I change this to an exponent, we get 7 to what power equals 1. Well, the only power that will make that work is 0, because that's one of those exponential rules. So that has to equal 0. So that's another rule. Anytime you have log base b of 1, it's going to equal 0. So whenever you see those, you really don't have to do anything. You should just be able to put it in. Okay, now if we look at number 7. So switch it to an exponent. So we have 5 to the some power gives us 125. Now, because it's in fraction, I know this is going to be a negative. And then, what is 125? Well, 5 times 5 is 25, times 5 is 125. So it's 5 cubed, so mine is going to have to be 5 to the negative 3. So my answer, negative 3. So that's the only way to make it look like that one. Because if you want to get it out from under there, we have to attach the negative to it. Okay, number 9, same idea. So rewrite it as an exponential. 2 to what power equals 32? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So it would be 32 is 2 to the 5th, so my answer is 5. That's what log base 2 of 32 is going to equal. So we're still using that same rule right down here. We're just now using it to help us evaluate those expressions. Alright, now expanding each logarithm. Now we have some rules here. We've got the product rule, the quotient rule, and the power rule. 3 rules. They're actually pretty simple to use. Okay, anytime I have multiplication, I know that I separate them and add. Anytime I have division, separate them and subtract. Anytime I have a power, bring the power down in front. So just looking at all the rules you have. So number 11. Now the first thing to probably pay attention to is that when 2 variables are next to each other, it means multiply. So I know I've got log base 2 of c to the 5th plus log base 2 of square root of 8. Okay, that's the first step. Now, are there any other rules I can apply? There's no other multiplication. There's no other division. So, powers. I have this 5 right here. And really, when I think of square root, I should really be thinking as the power to the 1/2. So I've got the 1/2, which would come down front, the 5. So it would be 5 times log base 2 of c plus 1/2 times log base 2 of a. Now, sometimes you'll see this one written as just log base 2 of a divided by 2. It's the same thing. Sometimes some programs like to write them that way more. Okay, number 12. We've got multiplication here. We've got powers, so same as 11. So log base 4 of x to the 5th plus log base 4 of y squared. Drop the 5 down, so it's 5 times log base 4 of x, plus drop the 2 down, 2 times log base 4 of y. Simple as we can get it. Now the last one's division, so we use the quotient rule. So log base 8 of x minus log base 8 of y. Nothing else I can do there, so we're done with that one. So you just look at those problems inside the parentheses, see what it is. Are they multiplying? Are they dividing? Are there powers? And then you just apply the rule. And sometimes you have to apply more than one, but you just do the same thing. Now on the flip side, we can take this piece and bring it back to the smaller one. Sometimes we only want to simplify it that way. Okay? But the same idea works. If you have plus, you know that becomes multiply. Minus becomes divide. Number in front multiplied becomes a power. So looking at number 4, we've got the natural logs here. I've got a 6 in front, so I know that's going to go up and be the natural log of w to the 6th. Plus, I know that divided by 2 could be rewritten as 1/2 times the natural log of u. So it would come up and be natural log of u to the 1/2. Or I could just realize 1/2 is really square root. So I could write square root, I could write 1/2. Doesn't matter. Okay, now it's plus, so we just combine them with multiplication. So natural log of w to the 6th times u to the 1/2. And if you want, put it in parentheses. Or natural log of w to the 6th square root of u. Okay, either one of those will work. Okay, 15. I've got 30 becomes a power, 6 becomes a power, plus we put them together. So basically log base 9 of x to the 30th times y to the 6th. That's how we simplify it. Now on 16, we've got a little bit more. Okay, so I've got 1/3, which would go up here, 1/3, which would go up here. Log base z stays the same, plus and plus, so we're multiplying. So I've got log base 8 of z plus log base 8 of x to the 1/3 plus log base 8 of y to the 1/3. So that becomes log base 8 of z times, now, x is 1/3, y is 1/3. That's cube root, right? So I can just put them together inside that cube root, just like that. That's probably the easiest way to do it. Alright, so condensing, you're just taking it back the other way. Same idea, you're just taking it back the other way. Alright, now use properties of logarithms and the values below to find the logarithm indicated. Do not use a calculator to evaluate the logs. So now we're using those same rules, but we're trying to simplify them to numbers we can use. So, 1/6. So I've got log base 7 of 1/6. Well, that would be log base 1 minus log base 7 of 6, right? Now, what did we say about anything to the first power? Right here, it's 0. So I know that this one is 0. Minus, do we know what log base 7 of 6 is? Yeah, they told us was 0.9. So 0 minus 0.9, negative 0.9. That's our simplified answer. So you just split it up into numbers you know. So like 18, 35. Well, that's 3 times 7. Actually, it's not 3 times 7. 5 times 7. Okay, we know what 5 is, so log base 7 of 5 times 7, we can change that to log base 7 of 5 plus, because of the product rule, log base 7 of 7. Now, we know anytime this is the same, we get an answer of 1. And log base 7 of 5 we know is 0.8. So 0.8 plus 1, 1.8 for our answer. So it's as simple as that. Okay, now on these ones, solving equations. Okay, the way to think through these ones is, if I have two logs that are equal to each other, and there's nothing else in their side of the equation, I can take what's inside the log and set it equal to each other. Okay? Because log base 15 and log base 15 are the same bases. So I know if they're equal, whatever is inside has to be equal. So I just get rid of the logs, and I solve for x. Okay, so we just eliminated those logs, because they're on both sides. What was inside we set equal to each other, and now we just solve. So I can add 6 to both sides, giving me negative 5x. Those cancel, equals 14 minus 3x. Now we need to get the 3x to the other side, so I add 3x. Get negative 2x equals 14. Divide by negative 2. And we get x equals negative 7. That's all you got to do. Here, natural log of 4x equals natural log of 5x minus 7. Well, let's get rid of those natural logs, and we get 4x equals 5x minus 7. So subtract 5x from both sides. We get negative x equals negative 7. Divide by negative 1, because we don't like the negatives. We get x equals positive 7. Okay, so when you see those types, that's all you got to do. Just get rid of the logs and solve. Okay, now let's take a look at the interest formulas. So we're given the formula A equals P the principal times 1 plus R the rate divided by N, how many times it's compounded in a year, to the N times T or time. Okay. Now if it's compounded continuously, our formula is this one, where we use that E value. A equals the principal times E to the rate times time. So, number 21, Ren Shawagami has $12,000 in a savings account. The bank pays 6.25% interest on savings accounts. Compounded monthly, find the total balance after 4 years. So, we've got 12,000, so that's our principal. We've got our rate, which is 6.25%, but remember, when we use it in math, we make it a decimal, so 0.0625. Compounded monthly, how many months are in a year? 12. And a time of 4 years. So it's simply just taking this information, plugging it into our equation, and then using a calculator to solve it. That's the easiest way to do this. Okay, yes, I could solve this stuff out and then times it, take it to the power, then times it by that. But honestly, it's all about just setting up the equation, pulling out your calculator, and getting things multiplied together. And the reason being is because a lot of these are decimals, and if you are rounding your decimal too early, it can affect your answer. So the best thing to do is to simply just type it into a calculator. I'm getting my calculator out right now. And I just type in 12,000 parentheses times 1 plus my fraction 0.0625 divided by 12. All of that is taken to the 12 times 4, which is 48. Or I can just write 12 times 4. Okay, and we get 15,398.31. Now, always round to two decimal places after because we're dealing with money. So $15,398.31. So they made, in those 4 years, $3,398.31. Not too bad. But that's all you're doing with these type of problems, is you use the equations to figure out the piece that's missing. Now, number 22. What is the final amount if you invest $3,000 for 40 years at 3.2 interest compounded continuously? So now we're using this guy. So our P is 3,000, T is 40 years, our rate is 3.2%, so 0.032. So I go A equals my principal, 3,000, times E, that special number, to the 40 times 0.032. So once again, put this in your calculator, okay? That's what we do with these kind of formulas, okay? So 3,000 times E to the 40 times 0.032. And you get $10,789.92 when you round. Okay, it doesn't seem like a whole lot in 40 years, but think, you only started with 3,000. You almost quadrupled your amount of money. So, not too bad, right? Alright, now 23 says, how many years would it take for you to double your initial investment of 2,000 at a 6% rate if it were compounded continuously? So compounded continuously, so we know we need that formula again. But this time, what are we looking for? How many years? So we want to figure out what T is. So it says our initial investment is 2,000. We want to double it. So that would be what? 4,000 would be our amount. And a 6% rate, so our R would be 0.06. So put in what you know. We know the A is 4,000 equals the principal, 2,000. E to the rate, 0.06, times the time. That's what we don't know. So now we're working backwards here. Okay, so when we're working backwards, this is where we're changing the focus. So instead of that exponential, we want to put it as a logarithm. So, but first we need to get rid of this number out front. So I'm going to divide by 2,000. So we get 2 equals e to the 0.06 times t. Now, this should look oddly familiar, like this one. So we change it to that. Change it to a log. So log base would be e, which we said was what? The natural log. So natural log of 2 equals 0.06 times t. Now we want to get rid of this 0.06, so we divide by 0.06. So I get natural log of 2 divided by 0.06 equals t. So we just put that into our calculator, and using that concept of the inverse, we're able to solve for t. So natural log of 2 divided by 0.06 gives us 11.5524. So about 11.5 years. That's our answer for number 23. Okay, so you're just working backwards and using that idea of the inverse with exponents and logarithms to figure it out. Alright, number 24. Mr. Radach has lived his whole life in the Twila area. Due to that, he has suffered contamination by the chemicals that the Twila Army Depot has been releasing since before he was born. Due to the change, or mutation, in his physiology, Mr. Radach now has a superhuman strength that grows as he gets angry. And I think I misspelled strength, didn't I? Yeah, transpose the H and the T. Mrs. Lorton, Mr. Lems, and Ms. Bates have studied this and realized that the growth of his strength follows this pattern where X is the amount of anger and Y is the strength exhibited by weight he can bench press. Using your skills with logarithms, given that Mr. Reynolds needs to lift 1,000 pounds, how angry does he need to get? Also include the equation for the other math teacher so they can look at how smart you are. So we've got a graph here. Okay, it's an exponential graph. So, what is this exponential graph? Because if you think about it, right, we are looking at the inverse. This is the anger. Here's the weight amount he can lift, the y-axis. So right now the anger is the input, which gives us the weight as the output. We want to flip that around and find that inverse so that we can do the same concept with our input being the weight, and then we can put that 1,000 in there and figure it out. So, thing you have to remember with exponentials, they're in this format of f of x equals a times b to the x. The b is the growth, what you're times them by, a is the y-intercept. Okay, so our y-intercept here is at 1, 0, 1. So a is 1, so this equation is f of x equals 1 times, now how is this growing? From point to point, how much are we growing? So this has a y value of 1, y value of 5, y value of 25. How do I get from 1 to 5, 5 to 25 with multiplication? We're times them by 5 each time. Okay, if I wanted to, I could easily make a table. 0, 5, 0, 1, 1, 5, 2, 25, 3, 1, 25, 4, 6, 25. If I keep multiplying by 5, I can even go backwards. Negative 1 would be 1/5. Okay? And if we want to find the inverse, remember with the table, we can just swap those. So you could go up until you got to 1,000 and figure out where you're at right here. That is one way you could figure it out. Okay, but they wanted an equation as well, so it's going to be easier if we write it like this. Okay, so 1, our y-intercept, times 5, how much it's grown, the number it's growing by, to the x, because we keep times them by 5. And the repeated multiplication in the shortcut is an exponent. Okay, now, we don't want to keep it this way, right? Because this isn't going to help us. Because it would be 1,000 equals this. And figuring that out is difficult. So, we have to get the inverse. So we switch this to a logarithm, right? Because when we find the inverse, we switch the output and the input, which is what happens. Look back here, right here. The output becomes the input becomes the output. Okay, that's why they're connected as inverses. So I would write the log base b, 5, of, and this times 1 doesn't really change anything, because we'd probably want to divide by 1 first, but dividing by 1 does nothing. So log base 5 of this output, which is going to become our new input, right, equals our output. Okay, so f of x equals log base 5 of x. That is the equation those math teachers want. That's part of your answer. Now we just need to figure it out for 1,000 for x. So I go log base 5 of 1,000. What does that equal? Okay, well, you could use those properties, simplify this, and deal with it that way, or you could just use your calculator and plug it in and see what that equals, which is what I'm going to do. And when you type it into your calculator, log base 5 of 1,000 equals 4.29203. So basically 4.29. So if you make me 4.29 angry, then I'm able to bench press 1,000 pounds. Okay, so that and that are your two answers. So some notes you may want to write down. You may want to write down how to figure out an exponential equation according to its graph, because that could prove important on the test. Alright, so we've got about 5 minutes left in here, so let's finish this up. So sketching the graph of a logarithm. Honestly, the easiest thing to do would be to type it in your calculator, find those points that are important, and go from there. But just so you know, the parent function of a logarithm looks basically like this, with that point right there, 1, 0, being very important. Okay, and if we think about the h and the k, we know how it's going to move, right? H moves on the inside, the opposite, so that would move it to the right 1. The k moves it up or down, would move it down 4. So it would basically look something like that. You could also make a table of values and plug numbers in and figure it out that way. That would work just as well. Okay? So let me show you on the calculator if you graph it what it would look like. So I type it exactly what it looks like in the calculator, and you can basically see we were pretty much spot on, weren't we? Pretty close. Alright, so now, how do we decide if two functions are inverse as kind of a review? Well, I can take this, find its inverse, see if it matches up to that, or I can do the f of h of x, where I plug in this for the value of x, then I solve it and see if it equals x. If it equals x, then I know it's an inverse. So let's try that. So f of h of x would equal negative 3/7 times negative 2x minus 4 over 3 minus 12 over 7. So I multiplied 3 on top, 3 on the bottom, they cancel out. Negatives and negatives cancel out. So I multiply across, and we get 2x plus 4 over 7 minus 12 over 7. Okay, now we can simplify that to be 2x plus 4 minus 12 over 7. That would be 2x minus 8 over 7. And we're pretty much out of luck right there, aren't we? So these are not inverses, because they didn't undo each other. Okay? Had they worked out, then it would have gotten, then it would have all disappeared and just become, you would have been left with just x. So, how do we find the inverse? Well, remember, make that function notation a y. That's easier to deal with. Swap the x and y, and then solve for y. So I'd add 2 to both sides, get x plus 2 equals negative 6y, divide by negative 6 on everything, and we get negative 1/6 x minus 1/3 equals y. And there's your inverse. Okay, 28, same idea. Make this a y, because it's just easier to deal with. Then swap the x and the y, so I get x equals 1/4 y plus 11/4 y. Then I'm going to times everything by 4 to get rid of those fractions. So we get 4x equals y plus 11, because the 4 cancels out. Subtract 11, and I get 4x minus 11 equals y. Okay, now in the remaining time, just to show you how it looks like when you check inverses, if I check these two, I would go f of the inverse of x. So I'd go 1/4, and for x I put in 4x minus 11 plus 11 over 4. That 4, if we multiply through, 1/4 times 4 is x. 1/4 times negative 11 is negative 11/4 plus 11/4. Well, negative 11/4 plus 11/4, that becomes 0. We're left with x. That's what it should look like. Okay, and if I put it in the other way around, so I've got 1/4, 4 times 1/4 x plus 11/4 minus 11. 4 times 1/4 is x. 4 times 11/4 is 11 minus 11. Those cancel out. We're left with just x. That's what it should look like when you have inverses. All right. So remember, these are two things very important to have written down. And I just wrote down a few more things. Okay. All this you want to have, possibly also that exponential equation one. So there you guys go. Make sure you are ready